we continue with series of lectures. Today he will give us some idea of what happens if you're trying to look at more than one eigenvalue at a time. Please.
Thanks, Nati. So far we started from some undirected graph. Assuming also that it's regular, which simplifies some notation, although doesn't affect almost any of the results that we talked about. So then we define this normalized Laplacian matrix. Which is symmetric, and we look at the eigenvalues of this matrix with multiplicity. We call them lambda 1 up to lambda in increasing order. So in the first two lectures we talked about what are the extremal and nearly extremal values for lambda 2 and lambda n, and what kind of properties of the graph can be derived from knowledge of lambda 2 or lambda n. So today I want to say more about what happens when you have some knowledge about additional eigenvalues of the Laplacian matrix. So first, let's look at the extremal case for inspiration. So we know that if lambda k is 0, G has k or more quantity components. So G admits a partition S1 through Sk of the vertices such that each Si has no edge going out. And if, say, lambda k is positive, then one thing we can say is that we can find no more than k quantity components, so we can find sets no more than k minus 1 quantity components. So let's call this k plus 1. So we can find, again, a partition S1 through Sk of the vertices such that each Si induces a connected subgraph, vertex-induced subgraph. Induces. So now the way we should think about the general case would be that 0 should transform to small, positive should transform to large. An isolated set of vertices should become a set of low conductance, and a set of vertices inducing a connected subgraph should be a set of vertices inducing an expanding subgraph. So now we know how to argue more or less each of these analogies. So as an analogy of the first result, it's known that for every graph G, though maybe in the case it's true for a partition, but it's also good to just think about generic subsets. So the G has k subsets S1 through Sk of vertices, disjoint, such that each of them has small conductance. if lambda k is small. And this is an if and only if. So if G has k subsets of vertices that are disjoint, and all of small conductance, then lambda k has to be small. So just as we can say lambda k is 0 if and only if there are k disjoint subsets, each with no edge coming out, we can say that lambda k is small if and only if there are k subsets, each with few edges coming out. Here few is not really counting the edges, but it's looking, when you can set Si, what is the total degree of the vertex in Si? So that's up to a factor of 2, how many edges touch Si. So having small conductance, like conductance epsilon, means that of this number of incident edges, only an epsilon fraction leaves the set. A 1 minus epsilon fraction stays inside. So in a graph, lambda k of the Laplacian can be small if and only if there are k subsets such that for each of them, almost all the incident edges stay inside. And you have the same kind of quadratic loss that you see in the Chigger inequality for lambda 2. In fact, this can be made to look a bit more like the Chigger inequality for k equal 2. So we could define this notion of order k expansion. Or maybe order k conductance. So it's at least the name will be the same when we go to the non-regular case. So here in the regular case, this would be defined the following way. For disjoint sets, S1 through Sk, their order k conductance is just the largest conductance. And then the order k conductance of a graph is the one of the smallest collection of disjoint sets. You can also define it for partitions. It will be the same up to a factor of k. Right, so this is saying if I want to find k disjoint sets, what's the best I can do in terms of making sure that each of them has few edges coming out? So then that result can be stated in the following way, that the order k conductance of G is at least lambda k over 2, and at most some point, is it just k squared? K squared. Square root of lambda k. So for k equal 2, this is just the conductance, the edge expansion, if the graph is regular. And so this is the Chigger inequality with a slightly worse constant. So here maybe for k equal 2, this might be 30 or 40 instead of being square root of 2. And for general k, it gives this kind of trade-off. So the only way for a graph to have small lambda k of the Laplacian is that there are several disjoint sets, each non-expanding. So for example, if your graph looks like this, that this is a highly expanding graph, this is a highly expanding graph, and then there's a small number of edges going across. This is a graph for which lambda 3 cannot be small. Because if it were, you would be able to find 3 disjoint sets, each non-expanding, but then one of those 3 sets would have to non-trivially cut one of the expanders, and then that set could not have small expansion. So this is sort of the robust analog of this fact. So we don't quite have a perfect analog of this. But we know several facts about graphs where one of the first few Laplacian eigenvalues is large, like larger than some constant. So one thing that we know is that many algorithmic problems that seem very hard to solve in the worst case for general graphs become considerably easier in graphs where lambda k is small for some k. So they become solvable in time that is exponential in k instead of being exponential in number of vertices.
So Luca, can you actually find these sets efficiently?
Yeah. So as usual, so this inequality comes from seeing lambda k as a relaxation. And this step is constructed.
So what substitutes this? Then you had this thing that you think of this as a mapping to the line, and you
Yeah, so we can...
if it's taking you off...
no, we can... actually, maybe just to make sure that I state all the things I want to state, I'll talk about various results, then I will see how many proofs I'll be able to give. So the difference will be that instead of mapping vertices to the line, you map vertices to a k-dimensional space. So for example, if lambda k is a sufficiently large constant times the expansion of the graph, then one can get a constant factor approximation. In fact, even a 1 plus epsilon approximation. If you want 1 plus epsilon approximation, this will have to be something like 1 over epsilon squared times the expansion of the expansion in time exponential in k. Maybe there's a polynomial. But in general, we don't know how to find the constant factor approximation of the expansion in sub-exponential time. In fact, if you could find a constant factor approximation of expansion in polynomial time in general graphs, that would refute the Unigame's conjecture. In this form, this is the Kurzweil-Missinov algorithm. I think in this form, one could get it out of Aurora-Barak's theory. Yeah. So there is also a sort of so one can prove a Fries-Canaan weak regularity lemma. For a graph G in which lambda k is large. So one can show that there is sort of a constant size model that depends on k and how large is lambda k that has a very good approximation of the graph in cut metric. And so that leads to the fact that one can approximate many graph problems like max cut in time only exponential in k in graphs like this.
Luca, just qualitatively, last time you showed us that lambda 2 is bigger than 0. If the graph is deregular, say lambda 2 is bigger than 0, you can only if the graph is an expander. Or if you only...
That lambda 2 is omega 1. Yeah.
For a family, lambda 2 stays above 0 for a family of deregular graphs, and you must have there must be expanders. This is, so is there an analogous result here? Maybe if lambda k stays above 0 for a family of graphs, is there some structural thing we can say?
No, so So one would imagine that the right analog would be to say if you have a family of graphs where lambda k stays like at least epsilon, it should be possible to find maybe to cover most of the vertices or even all the vertices with a bounding number of sets, each of them inducing an expanding subgraph. So we know how to argue some consequences of this, but in this form, the result is open.
Is there even one? Can you get one expander? Like, can you say that this must be because of an expander? In some sense.
So what would be the statement? That the subgraph is allowed, the graph is a allowed subgraph that is an expander.
Yeah.
Yeah.
I think you should be able to cover most of the vertices. I don't know about
With small expanders.
the induced expanders, but not K, maybe poly K or poly K. I think that's
Well, nothing of this has been claimed expansion. But what we can argue is the analog of this, that if lambda k is 0 and lambda k plus 1 is positive, so then here we have just exactly k quantity components.
Actually, you can have stronger thing if lambda k is really, if lambda k is 0 and if lambda k plus 1 is bigger than some constant, then you can say it's not only connected but has expansion there.
That's true. So, okay, so we can say that. Then one less extremal version would be to say if lambda k is 0 and lambda k plus 1 is epsilon, then in this case each quantity component has to be an expander. Because otherwise a non-expanding cut in one of those components would give you another, yeah.
What if lambda k is small and lambda k plus 1?
Yes, thank you. So this is the one. This is analog. This is something for which we have a good understanding. So if the order k plus 1 expansion is sufficiently larger than the order k expansion, in fact, I mean just a tiny bit more, then we can find, and this is can find suggests algorithmic, then there exists a partition of the set into k sets. Sorry, this is right? Yeah. Into k sets such that each of the sets has small outside conductance, which is bounded by phi k. Maybe there is a dependence in k here. And but also each set induces an expanding subgraph. Again, there is some dependence on k. So if you're thinking about these higher order expansions instead of thinking about the eigenvalues, even a small gap is giving you what you would expect. A partition of the vertices into subsets such that each set has few edges going out. But also, when you focus on that set, you see an expander. So that a partition like this can only be achieved in one way. Because like any other way of cutting the graph would cut those expanders and you would get sets of higher conductance. This is I mean, this relates to quantities that are NP hard to compute, so the proof itself is non-constructive. But if lambda k plus 1 is sufficiently bigger than the square root of lambda k, again with some dependence on k, then we can do the same. So here we cover all vertices with these joint sets, and each of them has small outside conductance that depends on lambda k. With some dependence on k, but large inside expansion that depends on lambda k plus 1. So this is the kind of partition that I think it was Fries, Cannon, and Vempala called the strong clustering. So something where you have a partition of the graph so that every cluster has few edges going out, but also it's minimal in the sense that when you look inside the cluster, there is no good way of cutting it. So if this is a graph that represents a similarity relation, and there is this kind of eigenvalue gap, this is saying that sets with this property should be possible to find. So all these dependencies are polynomial in k, but it should be possible, although we don't know, to get dependence logarithmic in k if one is willing to get some outlier vertices or some other kind of slackness in the condition.
Luca, can you say anything if the field grows slowly? So, for example, if you know that phi k is substantially bigger than phi l, but l is not one less than k, whatever, can you draw any conclusion from that?
No, unless we sort of interpolate and then find some I and I plus 1 where there is a gap, but then we lose too much in doing that.
So the no means we don't know, or we know that this is not true?
We don't know. We don't have a good sense of what kind of what would be good counterexample graphs to think about to see what's impossible. For now, we just try to. Yeah, we don't have a good sense of what's not possible in this setting.
Are you saying that's MD complete? I mean, you can prove this theorem, the one above the line. But it's NP complete to actually solve this problem or something?
To find this phi k or to find those partitions?
Yeah. I mean, I guess...
It was an or question.
Isn't finding the phi k and the partition the same thing? I don't know. So.
No, like, I mean, conceivably this could be approximated, I don't know. But the phi k themselves are at least as hard as expansion because you can always add isolated components. So, you know, I have some graph, I can make phi 4 be equal to the expansion of the graph that I started from by adding two isolated highly expanding components. So those numbers are hard. Those partitions, again, getting a constant approximation for phi k is as hard as finding a constant approximation for expansion. And again, I'm not sure if any of this has been written down, but I think you can get some maybe root log k, root log n approximation for phi k, like the natural extension of ARB. Has it been written up?
I think it's a result of Lewis and Tarcha.
So I heard of something like this some time ago.
Well, for partitioning though, it is written up by some subset of people.
Okay, so I heard it before it was official. So it's yeah. So you can get some approximation, but it's always at least as hard as expansion. So that's a bottleneck for how good things can be.
Luca?
Yeah.
Square root lambda k comes from Cheeger, I guess, or something. Or well, sort of your higher order Cheeger.
Yeah, I mean, again, you even just for one set, you wouldn't. Okay, so yeah, you wouldn't expect to do better than this without being able to do better than root lambda 2 versus expansion in the basic case.
Right, but I mean, so you have this other analysis of spectral partitioning where you get lambda 2 over square root lambda k.
Yes.
So is there something like that that holds here, that you can get lambda k over square root lambda k plus 1? Or
Right. So we can do that. Okay. Let me get to this. Okay. Right. So here is what we get out of a spectral gap. Again, if just lambda k is large, yeah, there is this idea that somehow one should cover the graph, should be able to cover the graph by expanders, but I don't know of a satisfactory result that says that.
I think there is if you don't put any constraint on the edges leaving the expanders.
If you don't put that, who is telling you that you are going to find some edge inside the expander?
No, I didn't say it's trivial. I just said that you partition the graph into things where the induced subgraphs are expanders, but you don't say anything about.
You're saying something like this is known or follows from things we know how to do?
I thought this guy Tanaka proved it.
Not without a gap, that I remember.
Okay, when you have a sequence of graphs and you know that lambda k is bounded from below, then somehow you get a gap somewhere because.
Okay. So then it will be there will be a loss that is like k to the k or even some tower.
I think it's possible to do the poly k loss. It was written down at some point.
But not published.
It was not published.
Okay. Well, now it's everybody knows. It's, we'll edit it before we post it online. So there is something kind of small that you can argue about this graph. That the diameter of a graph is at most, what is it, k times 1 over lambda k. I mean, if G is connected. Otherwise, this will apply to each connected component times log n. I mean, this is a two-line proof, but the reason why it's vaguely related is that suppose that you really have k expanders and that the graph is connected in some way. I mean, k expanders, somehow each of eigenvalue gap lambda k. Well, then you would expect that, so then each of those graphs, if it's really an expander with an expansion that depends on lambda k, each of these little graphs, or sort of induced subgraphs, would have diameter 1 over lambda k times log n. Because the diameter is always at most the spectral gap times log n. In fact, the mixing time is this much. But then you never need to hop through more than k of those expanders to go from anywhere to anywhere, so you would expect this upper bound. Right. So now going back to the fact that when lambda k is large, one thing we know how to argue is that that many problems become easier than in the worst case, is that if this intuition about the graph being made of k expanders plus extra edges is true, when you solve many convex relaxations of graph partitioning problems, say some kind of SDP, say the Gaiman-Williamson relaxation for max cut. Okay, that's the wrong example. Say the ARV relaxation of sparsest cut. Then in your solution, it will be not really advantageous to spread out your vector solution inside those sets, because then that would cost you a lot in the solution. So you'd expect the optimum of ARV or other convex relaxations for sparsest cut or other problems to concentrate their output in such a way that the vectors that vertices get mapped to concentrate in just in k small regions. So then if you go k levels up in the laser hierarchy, after conditioning you get a constant factor approximation. And in any case, you can still get something like log k or root log k approximation. That's much better than the worst case. And in fact, this kind of concentration of the solutions can be proved, even if we don't know exactly the expansion thing going on. What's that, Jeff?
No.
Right. So one more result I want to mention, and maybe I'll get back to this to answer Nati's question, is that this concentration of the solutions can be seen even in the spectral setting. So remember, the Chigger inequality for expansion says that the expansion of a graph is at most the square root of 2 lambda 2. And this is not just the expansion of the graph that is like this. It's that the best cut SB minus S that can be found just by taking a threshold to the eigenvector of lambda 2. And we know that in some cases this is best possible because even the best cut, not even the best cut that we find out of this argument, is really the square root of lambda 2. For example, in an n cycle, the expansion is 1 over 2 over n, because the best cut is this balance cut, and here we have, so there are 2 edges coming out, and then either side has n over 2 vertices, and what's that? And the volume is 2 times n over 2. But lambda 2 of the cycle is of the order of 1 over n squared. And one way to see that this is possible, this is not the actual eigenvector, but if you have your cycle, and so you can always think of an eigenvector as mapping the vertices on the line, and then the corresponding lambda 2, the corresponding Rayleigh quotient will be what's the average distance squared between endpoints of edges divided by the average distance square of random pairs of vertices. So if you okay, this is taking a while. Okay, so if you have your cycle like this, so let's say this is like minus n over 2, and this is n over 2. When you look at a random pair of vertices, it's a distance constant times n squared. Constant times n on the line. When you square it, it's constant times n squared. But every edge is a distance 1. So if this is your x, the summation over the edges of xu minus xv squared divided by d summation over v of xv squared. So the numerator will be order of n, and the denominator will be order of n cubed omega. So for some graphs, this inequality is tight. So that's sort of the integrality gap type instance for this relaxation. But this is a kind of solution that is possible for the cycle and many other graphs, in which the embedding produced by the eigenvector is very spread out. You don't see any kind of concentration of vertices in a few places. So instead, that's true in general. However, one can prove the tighter inequality. So here there is a fairly reasonable constant. And this applies not just to the best cut in the graph, but the best threshold cut using the eigenvector of lambda 2. And this is true for every k. So when you take k equal 2, this is just saying, well, it's at most root lambda 2. But if you have a graph where lambda 2 is very small, but say lambda 5 is very large, maybe lambda 2 is 1 over n, but lambda 5 is 1/10. This is telling you that the kind of expansion you're going to get will not be 1 over root n, will be 1 over n. Another way of putting it, that the approximation that you get out of this threshold cut algorithm will be the minimum over k of k over root log k. This might not be any better, because in some cases it cannot, than the standard analysis, but in graphs that have some kind of eigenvalue gap, it gives a better analysis. And the way this follows is similar to the way you get better approximation using semi-infinite programs when lambda k is large, which is that when lambda k is large, it will always be optimal for the eigenvector to concentrate points, not to spread them around. We'll give some intuition for this. So the idea is the following. First, we're given this. So we want to analyze how this threshold cut algorithm works. So this is the embedding in which we map every vertex v. So we're given this vector x.
Sorry, Luca, are we proving any of this kind of thing?
Okay, so now I want to give not the complete proof, but some idea of how you argue this. And then if there is time, I'll give some idea of how you argue that. So essentially, so in order to argue this, I need to show that when lambda k is large, there is some gain that I can make over the standard analysis. And this gain will come from the fact that if lambda k is much larger than lambda 2, it will be necessary for the eigenvector to not spread out the points too much, but to concentrate them. And then we need to argue that when the eigenvector concentrates points in not too many different places, then the analysis of the threshold cut algorithm can be improved. So how does the analysis of the threshold cut algorithm work? In general, first you are given this eigenvector. In fact, it need not be an eigenvector, just some vector for which the Rayleigh quotient is small. Then so you think of this as embedding the vertices on the line, so that every vertex v gets mapped to the point x sub v. And then every edge will gain a certain length. And the property that we have about x is that the average length square of edges in this embedding is small compared to the average distance square of random pairs of points. Good. So now the first thing we do is that we shift it so that the median of this embedding stays at 0. And then we look at which of the two sides by itself gives a better Rayleigh quotient, and we keep that. So let's say the positive side gives a better Rayleigh quotient. So this means that with no loss in the Rayleigh quotient, we just push half of the vertices to 0. So not to scale, these are the vertices at 0, and there are all the edges between them. So this will always be on one side of the cut. And we just need to decide how to get what subset of these other vertices to pick in our cut, and hopefully improve over the standard analysis. All right, so we have our vertices here and there. Now the first thing we'll do is to find a optimal k-means clustering of the line. So we want to basically partition the line into k blocks. And what we want to minimize is, for every block, what is the distance squared from the sum over the vertices inside the block of the distance squared to the closest barrier. So for a moment, I forget that there are any edges in this graph. I'm just looking at points on the line. And then I want to see if there is a way to, and then I want to look at some way of partitioning the line into k blocks that minimizes the max over the blocks of the distance square of each point to the closest barrier. So if the points were kind of clustered around in k positions, then I would want to pick the barriers like this. And if the points are very spread out, well, it doesn't really matter. It will not make much difference what I do. Maybe they will be evenly spaced. So in this case,
The barrier is the center of the cluster. It's very
yeah, you're right. Sorry, you're right. Because then later I will use those intervals. That's right. I shouldn't call them barrier. Yeah, these are centers. So I want to find k centers so that I minimize the max over the centers of the distance squares of the vertices. So let's look at the two cases.
You minimize the max of the sums?
I want to minimize over the choice of centers the maximum over the centers of the sum of the... So imagine that I just, after I pick the centers, I just want to move every point to its closest center. And then I want to find some way in which each center needs like not a lot of movement square for the vertices to get there. And so the optimum will balance the two things so that for every center it will be the same. Okay. So let's look at these two extremal cases, the well-clustered case and the poorly clustered case. So the thing is that in the well-clustered case, our eigenvector is very well approximated by a vector in which the entries take only k distinct values. Because instead of my vector x, I could construct a new vector for which every vertex gets mapped to its center instead of where it is. And that doesn't change things a lot. So maybe that's not the clearest way of expressing it, but I want to say, in this case, x is close to some vector such that there are only k possible values for its entries. in the poorly clustered case, I get that in each interval between centers, so this would be a very rough way of saying it, but each interval between centers, so an interval like this and an interval like this and so on, has a lot of points in the middle. Because sort of if the vertices were away from the middle, they would be close to the centers and we would be in the well-clustered case. So let's say this is case 1 and this is case 2. So then what we need to argue is that in case 1, the threshold cut algorithm works better than in the worst case, and that in case 2, lambda k is small. So then the two things balance to the threshold cut always working well when lambda k is large, and so the precise quantitative statement is like this. So why would you expect those two things to happen? Well, imagine that the points were perfectly clustered, so that already you just have one solution where the vertices get mapped to only k distinct values. So then you can do an analysis of the threshold cut algorithm that shows that you get a cut that costs at most k times lambda 2. So there is no quadratic loss in lambda 2, there is only a loss in k. I mean, the idea that doesn't work like this would be to say, well, I'm going to pick one of the k centers at random, and somehow one is right, and I have probability 1 over k of missing it. But something similar where the probabilities depend on the distance squared between the clusters work. And then you need a robust version of this that sort of mixes the Cauchy-Schwarz thing going on in the standard analysis with this idea of preferring to be at clusters. And then what you get is that there is an upper bound that is like k times lambda 2 times how much is the correction that you need to go from your vector to a vector with only k distinct entries. And then this correction so ends up giving you the 1 over root lambda k. Okay. So about case 2, why would you expect in this case lambda k to be small? So to prove that lambda k is small, you need to come up with a k-dimensional set of vectors, each with small Rayleigh quotient. But it's actually enough to come up with k disjointly supported vectors, each with small Rayleigh quotient. So k vectors, for each of them the Rayleigh quotient is small, but those vectors are non-zero in disjoint coordinates. So then everything in their span will also have small Rayleigh quotient up to a factor of 2. So we want to find, in the second case, k disjointly supported vectors, each with a small Rayleigh quotient, which means k disjointly supported embeddings of vertices on the line, such that in each of them, disjointly supported, that means k ways of mapping vertices to the line, such that when you look at what vertices are mapped not to 0, those are disjoint sets in each of the k cases. And also we want this mapping to be such that when you look at the distance squared of the typical edge, that's small compared to the distance square of the typical pair of vertices. So these are our constraints. And the idea will be that each of those intervals, we will exploit each of these intervals to get one of those vectors. And that what we will do for each interval is to construct a vector of small Rayleigh quotient entirely supported on the vertices in this interval. So then automatically we will get vectors of disjoint support. So the So the first thing that would come to mind if you want to do this would be to say, well, I want to get an embedding only of these vertices being non-zero. Everybody else needs to be 0. So you just sort of take this and map all the other vertices to 0. So this has the advantage when you look at what's going on with the distance square of edges, that the distance square of all the other edges becomes 0. That's good. The distance square of all the edges inside here stays what it is. That's good. But then if you have an edge like this, so maybe I'll blow this up. So this is the interval with the vertices, and you want to construct some new embedding. So this goes on a while in both directions. You want to construct some new embedding of the vertices on the line where those are the only vertices not mapped to 0. And so, as I said, the first thing that comes to mind is to take all the other vertices and put them to 0. But the problem is with edges like this. Because if you just take all those vertices and put them to 0, maybe 0 is really far away that way, now this edge becomes stretched a lot. Because this was like arbitrarily small, and now that vertex goes to 0. It's, so one way to avoid this is to do things with a smoother cutoff. So just saying I want to keep these vertices where they are and map everybody else to 0, it's a bit like saying I have this sharp, I have this indicator 0, 1 function, and then for every vertex I'm going to multiply what is the value of the vertex in the embedding by this cutoff function at its point. So then every vertex here gets multiplied by 0 and goes to 0. Every vertex here gets multiplied by 1 and stays 1. Now the problem with this sharp cutoff is that when you look at the difference between those 2 points after this multiplication, it can get amplified a lot. Right? Because this is a discontinuous function. So in a little interval, it can change a lot. So when you multiply two different numbers, you can get 2 very different numbers. So instead, you just want to do something like this. So that now the embedding is a bit harder to picture, but basically what you do is to take every vertex and multiply it by this smooth cutoff function. I mean, there are many smooth cutoff functions that would work. So all those vertices go to 0. Vertices close to this center also almost go to 0. Vertices here stay where they are. So the effect is that the vertices in this interval get spread out from here up to 0. Now what happens to the length square of this edge? Well, if this edge was small, the difference of the cutoff function at the endpoints is not very big. So even after multiplying by the cutoff function, you still have a short edge. Now the problem with this approach, and why you cannot do it in, then you could say, okay, I'll do it for every graph. I'll pick k intervals and then do a cutoff like this. But the problem would be if I had all the vertices very close to these endpoints. Now all the vertices will be mapped very close to 0. When I compute my Rayleigh quotient, this would be a problem for the denominator. Because in the Rayleigh quotient, I divide by the sum square of the vertices. So if I send them to 0, I'm making my denominator go to 0, and that's not good for the ratio. But that's precisely the case that is not happening here. Having all the vertices close to the centers is precisely not the case in which we are. That most vertices are away from the center. Yeah?
So you were able to use the structure of the lambda 2 eigenvector to argue something about the behavior of something higher in the spectrum, which is a priori sort of surprising, at least to me. Is there an intuition for what kind of information about stuff higher in the spectrum we ought to be able to extract from these very low eigenvalues? Like, it seems
Yeah,
like
it's I mean, those.
stuff should operate almost independently. So
Yeah.
it's sort of weird.
So if so somehow you can always look at vectors as witnesses that tell you something about the eigenvalues, even vectors that are not eigenvectors. Like if I give you some vector whose entries sum to 0 and whose Rayleigh quotient is small, then you can say, well, lambda 2 has to be small. So that doesn't need to be an eigenvector for this information to be there. Now what I'm saying here is that if I give you a vector whose entries sum to 0, whose Rayleigh quotient is small, and whose entries kind of spread out among the set of possible values, then I'm telling it's not just the witness that lambda 2 is 0. It's a witness that even that lambda 2 is small. It's also a witness that lambda k is small. Because I can take this vector and cut it up and smoothen out and do these operations. And then I will get k witnesses that together testify that lambda k is small.
Is there maybe something more? I just noticed if you took the eigenfunction on, like the kth eigenfunction on the line, and just drew it on top of your picture, then you would automatically get these. You would automatically get the functions you want.
Yeah, that's not my point. So if you look at the cycle, so that's a graph in which even lambda k is small, and so that's testified by k. So then it has these k eigenvectors, and
I wonder if you can just pull back the eigenfunctions from the cycle onto your graph and say that you have a k-dimensional space of functions on the cycle, and now because you have this nice embedding which says that your graph on average looks like the cycle or a path, then you can just pull them back as test functions.
who says that my graph on average looks like a cycle?
That you have a embedding. I mean, it's no worse than, because you have a nice embedding into a. It's not okay. You don't have to call it a cycle. You can call it but it's also an embedding to the cycle.
I mean, this looks like an eigenvector of the cycle, but my graph could. I mean, a grid embeds in pretty much a similar way when I look at the second eigenvalue.
Yeah, anytime you have this map from you can take the eigenfunction of the cycle and you can define a function on your graph. You can pull it back to your graph. It won't, in general, it just won't say anything, but it seems that here is kind of what you're doing, because you have a nice map from your graph into that.
Maybe you can explain it to me later. I think.
But graphs that are like Cartesian products, then this is not going to tell you anything about the whole other part of the space, like a grid or something like that, right? The square grid or a tree across a line or some other kind of thing. Because now you're only going to understand about one of the half, a small part of the graph.
Well,
Now you're only going to see all the vertices are going to be. There's going to be huge copies of vertices with the same value.
right, but so maybe the contrapositive of this argument is more illuminating. So it's not that we are looking at the eigenvector of lambda 2 and we are trying to understand something about the higher spectrum of the graph in general. It's more that we, in a sort of if and only if way, we're just saying unless the higher spectrum of the graph looks in a certain way, we are going to see that the eigenvector of lambda 2 is going to look like that. And that helps the the threshold cut algorithm. So whenever the eigenvector lambda 2 is not looking like this, but it looks like that, we cannot say that we understand the higher spectrum. We just say there is a sort of slow eigenvalue growth. There is no eigenvalue gap. So this is true for. So when you just look at this eigenvector, it looks almost the same for a cycle and for a grid. So you're right that you cannot tell the difference between a cycle or a grid just looking at this. Or even if you have a real grid, or if you have a real grid where these edges have very small weight, which is one of the bad cases for threshold cut. Somehow they will all pretty much look the same. So what we can say in that case is just that there is a slow eigenvalue growth. So it's another case why we can always do better in finding a cut, because either things are concentrated and a cut does well, or else we have some understanding of the higher spectrum and then we use that to do something. We're just saying either the eigenvector looks like this, and then we can do a better analysis of the threshold cut algorithm, or there is slow eigenvalue growth. That's a very generic information, so that's all we got. So that's why the interpretation for us is the contrapositive that says, suppose you are promised that there is an eigenvalue gap, well then the threshold cut algorithm will work better than in the worst case. So I think that's the direction that makes more sense. Okay, so I guess time is up, but if there is any more question?
Let's first.
I mean, you should explain something like a bad example, because I think people don't understand that, you know, in processing image, you know, doing image processing, you know, the